Welcome to today's session on physical and chemical properties of materials. We'll explore the characteristics that define material behavior and understand how these properties influence engineering design and performance. In this session, we'll start with an overview and objectives, followed by the agenda. Our goal is to understand key material properties and their practical implications. This presentation introduces 9 fundamental aspects of material properties that influence engineering design and performance. The objective is to provide a clear understanding of physical and chemical properties, their measurement, and their impact on applications. We will explore how these properties guide material selection, affect reliability, and determine suitability for specific environments. The session emphasizes practical examples, charts, and diagrams to illustrate concepts such as density, thermal and electrical behavior, magnetic characteristics, and corrosion mechanisms. By the end, participants should appreciate the interplay between these properties and be able to apply this knowledge in real-world scenarios. The agenda covers: Number 1, physical versus chemical properties; Number 2, phase transformation temperatures; Number 3, density; Number 4, specific gravity; Number 5, thermal conductivity; Number 6, thermal expansion; Number 7, electrical conductivity and resistivity; Number 8, magnetic permeability; Number 9, corrosion. Additional slides will address applications, testing standards, and key takeaways. Each topic includes diagrams and speaker notes to facilitate understanding. Let's begin with the distinction between physical and chemical properties. Physical properties can be measured without altering the material's chemical composition. Examples include density, thermal conductivity, electrical resistivity, magnetic permeability, and thermal expansion. These properties often depend on microstructure, temperature, and phase distribution. Chemical properties, on the other hand, describe how a material reacts or changes composition under certain conditions, such as oxidation, corrosion, or flammability. Understanding both sets of properties is essential because they often interact. For instance, corrosion, a chemical process, can degrade physical properties like strength and conductivity. Engineers must consider these interactions when designing components for durability and performance. Next, we'll look at phase transformation temperatures and density, which are critical for material selection. Phase transformation temperatures include melting points for metals and ceramics, glass transition temperatures for polymers, and Curie points for magnetic materials. These temperatures dictate processing conditions and service limits. Materials with high melting points, such as ceramics, are suitable for high-temperature applications, while polymers with low glass transition temperatures are limited to low-heat environments. Designers must ensure that operating temperatures remain below critical transformation points to avoid dimensional instability or loss of mechanical integrity. Density or ρ is mass per unit volume and influences weight, inertia, and structural performance. Typical ranges: polymers, approximately 0.9 to 1.4 grams per cubic centimeter; aluminum, about 2.7, steel, around 7.8, copper, roughly 8.9, and ceramics, between 3 and 6. Specific gravity is a dimensionless ratio comparing material density to water, which is about 1.0 grams per cubic centimeter. Specific gravity is a dimensionless ratio comparing material density to water, approximately 1.0 grams per cubic centimeter. It is useful for quick buoyancy checks and material identification. Low-density materials are favored in aerospace and automotive applications for weight reduction, while high-density materials are chosen for radiation shielding or vibration damping. Thermal properties include conductivity and expansion, which influence heat management and dimensional stability. Thermal conductivity, or K, measures heat transfer capability. Metals like copper, approximately 400 watts per meter per Kelvin, and aluminum, approximately 205 watts per meter per Kelvin, are excellent conductors, making them ideal for heat exchangers and electronics cooling. Ceramics and polymers have much lower conductivity, suitable for insulation. Heat transport occurs via electrons in metals and lattice vibrations, phonons, in ceramics and polymers. Designers must consider thermal conductivity for managing heat flow, preventing overheating, and ensuring thermal stability. Thermal expansion describes dimensional changes with temperature. The coefficient of linear expansion varies widely: polymers, 50 to 200 micrometers per meter per Kelvin, aluminum, approximately 23, copper, about 16.5, steel, around 12, and ceramics, roughly 6 to 10. Mismatch in alpha between joined materials can cause stress, warping, or failure. Engineers mitigate these effects by selecting compatible materials, adding compliant layers, or designing expansion joints. Thermal expansion is critical in electronics, aerospace, and composite structures. Electrical conductivity and magnetic permeability are vital for electronics and electromagnetic applications. Electrical resistivity or ρ and conductivity, sigma, are inversely related, sigma equals 1 over ρ. Metals like copper and aluminum have very low resistivity, making them ideal for conductors. Steel and titanium have higher resistivity, while polymers and ceramics are insulators with resistivity approximately 10 to the power of 14 ohm meter. These properties influence power loss, signal integrity, and heating. Temperature and impurities affect resistivity, so designers must account for operating conditions. Magnetic permeability or μ indicates how a material responds to a magnetic field. Relative permeability, μ sub r, is near 1 for non-magnetic materials like aluminum and copper, while ferromagnetic materials such as steels and ferrites have μ sub r values from hundreds to thousands. Applications include transformers, inductors, and magnetic shielding. Above the Curie temperature, ferromagnetic materials lose their strong magnetic properties, becoming paramagnetic. Corrosion is a chemical degradation process that affects durability and performance. Corrosion is a chemical degradation process driven by environmental factors such as moisture, salts, and temperature. Types include uniform corrosion, galvanic corrosion, pitting, crevice corrosion, and stress corrosion cracking. Galvanic corrosion occurs when dissimilar metals are electrically connected in an electrolyte, causing the more active metal to corrode. Prevention strategies include selecting corrosion-resistant materials, applying protective coatings, using inhibitors, and designing to avoid crevices. Cathodic protection and sacrificial anodes are common in marine environments. Let's see how these properties influence material selection, testing methods, and standards. Applications illustrate property trade-offs. Heat exchangers require high thermal conductivity and corrosion resistance, favoring copper or aluminum alloys with protective coatings. Aerospace structures prioritize low density and high specific strength, leading to aluminum, titanium, and composites. Electronics demand high electrical conductivity for interconnects and controlled magnetic permeability for shielding. Process piping in chemical plants requires corrosion-resistant alloys such as stainless steel or nickel-based materials. These examples show how multiple properties must be balanced for optimal performance. Property measurement follows standardized methods: density and specific gravity via Archimedes' principle or pyknometry, thermal properties using differential scanning calorimetry or DSC and dilatometry, electrical resistivity with 4-point probe techniques, magnetic properties through B/H loop analysis, corrosion resistance via ASTM G series tests, salt spray or ASTM B117, and electrochemical methods. Standards ensure reproducibility and comparability, enabling engineers to make informed decisions based on reliable data. Finally, let's summarize key takeaways and point you to references for deeper study. Material properties are interdependent and influenced by microstructure, temperature, and environment. Designers must consider trade-offs among density, thermal and electrical behavior, magnetic characteristics, and corrosion resistance. Compatibility between joined materials, life cycle performance, and cost are critical factors. Testing and adherence to standards validate property data and ensure reliability. Integrating these considerations early in design prevents failures and optimizes performance. Recommended references include Callister Rithwish, Materials Science and Engineering, An Introduction, Shackelford, Introduction to Materials Science for Engineers, ASM Handbook Volumes on Properties and Corrosion, Ashby, Materials Selection in Mechanical Design. These sources provide comprehensive data, methodologies, and case studies for deeper understanding.